Hello, welcome to the Stereochemistry and Optical Activity Lab. In this video, I will show you how to determine the optical activity using a polarimeter. Recall that a pair of enantiomers, R and S, are each chiral molecules, so they are different compounds, but they may have the same chemical and physical properties, such as the same molecular weight, same boiling or melting point. So the question then is, how do we differentiate one enantiomer from the other? Well, each enantiomer will rotate the plane of polarized light in opposite directions because they each have different spatial arrangements. And this ability of molecules to rotate plane polarized light can be observed using a polarimeter shown here in this picture, where you will have a light source and then you'll have two filters, a polarizing filter and an analyzing filter that you can rotate, and a sample holder that will contain your chiral molecules. So what a polarimeter does is that it measures by taking light, polarizing it, and then the sample rotates the plane of polarization, and the second filter will be used to determine how much this filter needs to be rotated until no light is passing. And so to quickly review, if you have a sample containing one enantiomer, either that be a pure R or pure S, it is said to be optically active. And this compound and its enantiomer will have equal but opposite optical rotations. Meanwhile, if you have a 50-50 mixture of each enantiomer, of each R and S, it's called a racemic mixture, it's going to be optically inactive. And likewise, compounds with no chiral center will also show no optical activity, so they will also be optically inactive. And then on the other hand, if you have a mixture of two enantiomers that are not in a 50-50 ratio, it will lead to a partial cancellation of optical activity. And by using a polarimeter, we can experimentally determine the optical purity of a sample like this, and then also use these equations. So this is what our polarimeter in the lab will look like. Here is our lamp or our light source, and then the dial that you can rotate, and then at the top to see the appearance of light passing through. And here is our sample holder. So you want to first determine the 0 point. This is just the standard or the solvent. You will place the cylinder containing your solvent in the sample slot holder, or leave the polarimeter empty if your sample is a pure or neat sample. Next, you want to turn on the light source, making sure that you don't move this around as you take your readings, or else you will get inaccurate reading. As you focus in at the top, next you want to rotate the dial until it begins to turn dim. So after rotating, it's getting dim, or as it appears purple here. You want to keep rotating until you find the darkest point, and then you want to record that value as your 0 point. After finding your 0 point, you're going to next place the cylinder containing your sample into the sample holder. Now, this sample may be in solution, or it could be a neat or pure sample, or a solution that you may have to prepare as indicated. And again, you want to measure the rotation by turning on the light, rotating the dial until it turns dim. And so a common mistake would arise if you rotate in the wrong direction. So the first thing you want to do is you want to first try switching between rotating a little bit to the right or a little bit to the left and determine which direction it began to dim. And then you're going to want to keep rotating in that direction until you actually find the darkest point. And then after you find the darkest point, you're going to record this value for your measured sample. So again, you're going to see a bright light, and then it appears dim. And you also want to make note of the direction in which you rotated. So make note if you rotated to the right or clockwise, it'll be positive, or counterclockwise would be negative. So another mistake could also arise if you over-rotate or you rotate it in the wrong direction. So you just want to be careful if you're rotated past 180 degrees angle, because your light will only rotate plus or minus 180 degrees, and so over-rotating would mean that your rotation should have been the opposite direction. So just watch out for this. So for reference, here is our 0 point at 314, and then our sample at 254. And so the difference between your answer would be your observed rotation. And then next, for every sample, you will also need the concentration in grams per mils. For pure samples, this is going to be just the density. And you also want a path length. So you just want to take a ruler and then measure the length of your solution. And that's it. So say our final measured value for the sample was 254, and say our zero value was 314, and we would need to subtract this, and then because it was rotated counterclockwise, so it makes sense that our observed rotation is -60. So once you have your observed rotation, we can then put this into the formula for determining specific rotation, which is specific to a molecule and can be determined from these factors. So specific rotation, alpha in brackets, is equal to alpha observed, or the observed rotation, divided by the path length in decimeters times the concentration in grams per mil. So as we plug in our values, so say we have 1 decimeter, and then the sample's concentration, we would get -62.5 our specific rotation. If the solution is prepared, this concentration will be given to you, or if you're making a new solution, you want to make sure you record the experimental amount, and you'll have to convert as needed. So to complete the lab, you may be provided with different types of samples to determine the observed rotation, or then to determine the specific rotation, or the percent enantiomeric excess or optical purity of a sample. So for instance, you could be given a sample that is one just a pure R, and then you could be given another one that's the pure S of that compound. So recall that one enantiomer will rotate plane polarized light in one direction, and the other will rotate light in the opposite direction. You can experimentally determine the observed rotation just as before, and then use the equation to calculate specific rotation. On the other hand, you could be also given a racemic mixture where you will have 50% R, 50% S. And so conceptually, if every molecule trying to turn light to the right will be cancelled out by another trying to rotate it to the left, so you can actually think and predict about the expected specific rotation for this type of sample. And next, consider a hypothetical mixture of enantiomers with 70% S and 30% R. Now the enantiomeric excess is basically just the percent of what remains of an enantiomer that we had more of, and that's just going to be the difference. So for example, we will subtract 30 from 70, and we'll get 40% enantiomeric excess of the S enantiomer. But then say you may also be given a sample containing a mixture of R and S, but you are not given the ratio. So if you're given the sample with an unknown ratio and then asked to determine the optical purity, you will just use the result from polarimetry to get this optical purity, which is basically just the ratio between your sample's specific rotation and the pure enantiomers, or the pure solution's specific rotation, and multiplying this by 100. So this is basically numerically equal to enantiomeric excess, but it will be just experimentally determined.